So this is where Coulomb was able to come up with something that we call Coulomb's law. So he basically said the electrostatic force between two charged objects is directly proportional to the product of their charge magnitudes and inversely proportional to the square of the distance between them. So all of this is really meant to say that the law that Coulomb came up with actually looks very, very similar, actually exactly the same as Newton's law of gravity. In fact, they're very, very analogous, and the mathematics that's used in order to calculate them is actually basically the same. So if you take a look here, this is Coulomb's law. Here is the electrostatic force right here. Oh, that didn't look very good. The electrostatic force, and here we have a constant K, which is known as Coulomb's constant, of course. And here we have Q1 and Q2. Those are the electric charges. So we call those charges. And then down here we have the distance between the two charges. So that's our distance. There we go. So notice that this looks almost exactly the same as Newton's law. Newton had his famous equation was force of gravity is equal to big G m1 m2 over r squared. So it looks exactly the same. And so hopefully that will help you guys to remember that the math between two charged objects is exactly the same as the math between two massive objects that have mass. So if you want to calculate the force between two objects that have charge, it's just like calculating the force between two objects that have mass. So if we wanted to look at how we can actually do this, we have our electrostatic force right here. Electrostatic force. Where's my pen? There it is. Electrostatic force is equal to Coulomb's constant times charge 1 times charge 2 divided by the distance between them squared. So that means that if I have two charges, such as I have down here, I have a negative charge and a positive charge. If I want to find the force between them, the magnitude of that force, and remember the magnitude just means the size of the force, how big is the force, it's going to be taking the charge of the first one times the charge of the second one divided by their distance squared times Coulomb's constant K, which I'll show you shortly. And that's going to give you the magnitude of the force. Now, each one of these charges feels the same force. Remember, that's just Newton's third law. So F21 is the force of charge 2 on charge 1, and F12 is the force of charge 1 on charge 2. They're both exactly the same in size, they're just pointed in opposite directions. Remember, Newton's third law says that every force has an equal and opposite force that pairs with it. So this is a Newton's third law pair. The forces are felt by the same objects, just in opposite directions and on opposite things. Down here, you can see that we have a very similar setup, except this time we have both negative charges. So remember, like charges repel, and similar charges, or sorry, opposite charges attract. So here you can see that for this setup up here, the forces between the two charged objects are pulling towards each other. It's an attractive force because they're opposite. And down here on the bottom, we have an opposing force or a repelling force because we have the charges that are actually the same. Oh, there we go. So we say that charge is quantized because quantized comes from the word quantity. It means that charge only takes place in specific discrete values, meaning that it's not a continuous type of flow. So we could say that the charge of an object must fall on certain discrete steps. There's no in between. So we have what's called the fundamental charge, which is the charge on a single electron, and we can only get multiples of that single charge. We can't get anything in between. So you can have the charge of 1 electron, 2 electrons, 3 electrons, 4 electrons, etc. But it's impossible to get a charge that's 1.5 or 2.3 or 4.8. There's no such thing as a fractional charge on an object, on any object, because charge only exists as small as the charge on an electron. An electron carries what we call the elementary charge, or the fundamental charge. So the value of that is, there we go, negative 1.602 times 10 to the minus 19 coulombs. And of course, it's named after our guy Coulomb. So the fundamental charge, the smallest possible charge that can exist in the world, in the universe, is 1.602 times 10 to the minus 19 coulombs. Now, an electron has the negative version of that charge, because an electron is negatively charged, and a proton has the exact same charge, just the positive version. So we call E the electrical charge, and an electron has a charge minus E. And so then a proton would have a charge plus E. Okay, so continuing on with Coulomb's law, we want to look at Coulomb's constant K. Now, unfortunately for Coulomb, he did not find the actual value of the constant before he died. But since then, through experimentation, we've been able to figure it out. And it's equal to 9 times 10 to the 9 newtons meters squared per coulomb squared. I know it's a really complicated unit, but don't worry. You're going to have those available on your formula sheet on the test, so don't freak out. This is Coulomb's constant. It's got a really complicated set of units. 9 times 10 to the 9, though, isn't too bad of a number to remember. It's also equivalent to 1 over 4 times 1 over 4 pi epsilon naught. Now, oh, by the way, the value of K is much larger than the gravitational constant. If you remember back in the beginning, when we were first talking about the introduction to physics, we talked about the different fundamental forces that were involved in the universe. And we talked about how gravity is actually the weakest of all the forces. Well, if you remember, the value of G was 6.67 times 10 to the minus 11. It's really, really tiny. But here you can see that K is much bigger. It's times 10 to the positive 9. It's like 20 orders of magnitude larger. That shows you that the inherent value of the force of the electric force is 20 orders of magnitude larger than the force of gravity. It's massively larger. It's ridiculous how much larger the force of electricity is than the force of gravity. Gravity is actually incredibly weak. And one of the stronger forces that we have is actually the electric force. And it's something that we interact with on a pretty regular basis. So that's a really interesting tidbit that scientists and theoretical physicists are actually still kind of investigating as they try to find theories that kind of unify all the different forces in nature. And it's really fascinating to scientists why the force of gravity is actually so weak. But anyway, so the value of Coulomb's constant can be written as 1 over 4 pi epsilon naught. And if you guys remember, we talked a little bit about what that word means. Naught is the same as saying nothing or 0. So in other words, you see that little 0 there at the bottom of the epsilon naught. That's basically saying epsilon is a special kind of quantity that's known as the permittivity, which is basically saying how susceptible is a certain medium to an electric charge. So the permittivity of any object or any material tells you how well the electric field can travel through that space. So epsilon naught is known as the permittivity of free space because in a vacuum, there's no material. So it's kind of like your baseline permittivity, the permittivity of nothingness. So this value tells us in a perfect vacuum, if there's nothing in the way, it scales how far or how strong the electric force can be felt from an electric charge. Now this value changes when we include different objects or different materials. So since it's no longer a vacuum, the value of epsilon begins to change, and it's no longer epsilon naught, it's just epsilon. But for at least for now, and for most of the stuff that you guys will be doing, we won't have to worry about a different kind of epsilon. So just stick with epsilon naught and know that it's the constant that tells us how strong the electric force can be inside a vacuum with no other material present. And there is the value of epsilon naught. It's really tiny, but since it appears on the bottom of the fraction, that makes the value of Coulomb's constant really big. So it's 8.85 times 10 to the minus 12, and it's just got the opposite units of Coulomb's constant. It's Coulomb squared over Newton meters squared. And of course, here is Coulomb's law in terms of epsilon naught. So this whole thing right here is just Coulomb's constant K. So depending on how you want to do it, you can either use Coulomb's constant by itself, or you can do 1 over 4 pi epsilon naught.